Grade 11 Chemistry, this is 1.6. We're talking about properties of ionic and molecular compounds. Let's see what we're talking about today. First, we're going to talk about electronegativity and what that means for polarity. Then we're going to talk about the ionic lattice and what that means for the properties of ionic compounds. We'll talk about covalent structures and what that means for the properties of covalent compounds. And we'll talk about the specific properties that we're interested in, which is boiling points, solubility, and this concept of electrolytes. So let's jump in and talk about the electronegativity and the polarity. So I'm going to bring my stuff back up here. So kind of the first question is, why do nonmetals steal from metals, and why do nonmetals and nonmetals share? There must be some kind of reasons, some kind of difference. Why do we even have this talk of metals and nonmetals in the first place? And as you can imagine, based on the current topic, electronegativity is going to enter into it. So let's remember what electronegativity is. It's this pull for outside electrons. It's how strongly a atom wants an electron from somewhere else. And just think about it for a second. Which ones will have a higher electronegativity on average? Think about your trend in the table, and you'll know that it's the nonmetals. The nonmetals have the highest electronegativity, so they have a strong pull for outside electrons. Meanwhile, the metals have a relatively weak pull for outside electrons. So this helps us explain why nonmetals can steal from a metal. The metal has a weak hold on its electron, a weak pull, and the nonmetal has a strong pull. So what you end up with is that the nonmetal can fully rip an electron away from the metal because the metal doesn't have that strong hold. Meanwhile, nonmetals and nonmetals, it's two nonmetals. They both have a strong pull. So you end up in this kind of tug-of-war situation where both of them are going to be attracting the electron, and you'll end up in a covalent kind of bond. I like to call it kind of a tug-of-war. It's not really a tug-of-war, but it's a good visual for what's going on. So it's all about electronegativity, and wouldn't you know it, we have these general rules about how this can go. So this is what we call polarity. Polarity is how imbalanced the pull on this electron is. So if you go back to the tug-of-war thing, right? If you have one side pulling more than the other, it's going to pull harder one way than the other way, and that will lead to something called a polar bond, right? A polar bond, where the electron spends more time on one atom than it does on the other because this atom might have a stronger pull, a stronger electronegativity. It's measured as the difference in electronegativities. So when you have something that's polar, this would be stronger than this. This might be maybe oxygen, and that might be hydrogen or something like that. Meanwhile, a non-polar covalent bond, there's no preferred side, so that would be maybe two of the same atom. And it could be two atoms with a strong pull, like two fluorines in a fluorine molecule. It could be two atoms with a weak pull, like two hydrogens in a hydrogen molecule. It would give you the same kind of shape. And then down here is an ionic bond, right? A full separation of charge. That would be if this was a very strong pull and this was a weak pull. So this might be a non-metal and that might be a metal. So that might be chlorine, that might be sodium. I'm going to pause and set this up in a little program called MolView. Here I am in MolView, and you've seen I've made an HH, a ClCl, an HCl, and an Na plus Cl minus. What we're going to do is we're going to go to 3D, like this, and here they are, HCl, ClCl, HH, and Na plus and a Cl. Oh, so that must be an Na plus, the purple, and this must be a Cl minus, the green. And what we can do is actually do this thing called energy minimization, and we'll see, hopefully, I'm going to calculate. And hopefully these two will get attracted to each other if I hit energy minimization a couple of times. No? I guess it doesn't want to. That's okay. What we can do instead of that is actually hit this, which is surface opaque. And what it'll give us is this kind of cool 3D cloud look at these atoms. And what you can see is this is just kind of a lump. It kind of looks like a lumpy potato. This looks like a bigger lumpy potato. Here, though, the electrons aren't evenly distributed. You've got more electrons around the chlorine and fewer electrons, or less electron density, what we call it, electron density, around the hydrogen. So that would be a polar covalent, right? This kind of thing, a polar covalent bond. You see there's more electrons on one side than the other side, more density on one side than the other side. Then this is a full positive, and this is a full negative. A full positive and a full negative. And you see that there's a completely different charge density there. It's kind of fun to look at this for water. Here's water. Right, the oxygen has a very strong pull for electrons. It's way up in the top right corner. The hydrogen has a lot smaller pull for electrons. If I hit this, you see the red is where there's a lot of negative, and the blue is where there's a lot of positive. And so you'll see that the electrons really like to stay with the oxygen and a lot less with the hydrogen. So you get this polar covalent bond on two sides. So that's electronegativity and polarity. As you can imagine, we have numbers for this. These are the typical numbers. If you have a difference in electronegativity, mind you, a difference in electronegativity of more than 1.7, you get ions. So sodium, if we look at our electronegativity table, is about 1, and chlorine is about 3. So 3 minus 1 is 2. The difference between the two of them is 2. The tug of war is unequal by this factor of 2, and so that's enough for the entire electron to get ripped away. This depends heavily on the size and the environment that these ions are formed in. So it's not perfect, but it's a pretty good guideline. Polar covalent, that's that uneven tug of war kind of setup here, is a difference in electronegativity between 0.4 and 1.7. So hydrogen is about a 2.2 and chlorine is about a 3. That's a difference of about 0.8. And so that tells us that it's going to be uneven like that. Or hydrogen 2.2, oxygen 3.5, the difference is 1.3, which is very highly polar. And that's what we see when we look at our water, this highly polar kind of bond. In fact, we can actually see the bond dipoles. They'll actually show us which way the electrons want to go. These arrows show us that it wants to go towards the oxygen from both hydrogens. Nonpolar means there's not much difference. Electrons are shared evenly, and we call that less than 0.4 in terms of an electronegativity difference. So the curriculum actually wants you to know these numbers and wants you to be able to predict what kind of bond will be formed between two atoms based on their difference in electronegativity. Alright, we're getting into ionic solids. I'm going to pause and fix up my stuff. For this section, we're starting off back in mole view, and I've got a bunch of positive sodiums, a bunch of negative chlorines. We're going to see how the energy minimization deals with this. So there's a bunch of positives and a bunch of negatives. Notice they're all in a row. A lot of positives in a row, a lot of negatives in a row. I'm going to hit energy minimization, and we'll watch them kind of move around. Watch them kind of wiggle and move, and weird stuff starts happening in the center there. They're starting to kind of migrate towards each other. We'll do it again. And we can watch these guys kind of arrange themselves. This is the program's just doing a bunch of electric force calculations and trying to balance the attractions and the repulsions of each of these guys. And you can see them kind of organizing themselves in interesting ways. And we'll hit this a couple more times and we'll see what comes out. I can already kind of see the arrangement happening. I don't know if you can. That's kind of the best look at it. So you can see it's shaking and trying to arrange itself. But notice what happened from that lineup. they started self-arranging into this kind of grid thing where it's they're opposite each other, and it's positive, negative, positive, negative, positive, negative. If you imagine billions of these, because every time we have a salt crystal, we have billions and billions and billions of these things. You can imagine it's going to be positive, negative, positive, negative, positive, negative, and then the other way, positive, negative, positive, negative, positive, negative. And we were doing this for energy minimization because we want to balance our attraction and our repulsion. So eventually you end up with something like this. This is called a lattice, and a lattice is an arrangement of positive and negative charges where it is the minimum energy possible, essentially. And here you see chlorines and sodiums arranged in a perfect cube, with every chlorine surrounded by sodiums and every sodium surrounded by chlorines. This is the lowest possible energy for the salt lattice. Now, cubic isn't the only possibility for a lattice. There's a bunch of different ones. Like here's the salt cubic lattice, but then there's kind of stuff like this or like this or like this. There's interesting differences, and that actually leads to the shape of different crystals. If you ever looked at a crystal, sometimes they have like kind of pointy ends. Sometimes they're more square. That comes from these kinds of arrangements. Based on relative size and stuff like that. Right? This is also why ionic compounds are so hard. They're very, very hard, but they're often quite brittle. So, for example, salt is very, very, very hard, but if you hit it with a hammer or something, or if you grind it, it'll crack apart very easily. Same thing with chalk. Chalk is also an ionic compound, and it's also quite brittle. The hardness and the brittleness both come from the same thing. It's these forces of the ions in the lattice. It's all ionic. It's all positives and negatives. So when the positives and negatives are all lined up nicely like this, it's a very strong, held together object. But if you push it even a tiny bit out of alignment, it's very difficult to push it out of alignment because of the strength of the force. But once you do, then instead of positives and negatives attracting each other, you suddenly get positive, positive, negative, negative, positive, positive, negative, negative, and that's suddenly a repulsion, and the crystal will break. And we call this cleavage planes because it comes through as a perfectly linear crack through the crystal. I'm going to pause and find a nice example of this. Here's a great example, just found it on Google Images. It's a calcite crystal, and you can see how it broke in these perfect planes, these perfect cleavage planes. Those are places where the crystal got knocked out of alignment by one atom, and you get these beautiful beautiful cracks that open up in the crystal. This actually helps geologists figure out which mineral it is. They'll look for the directions of the cleavage planes. There's also a good example of a crystal that isn't cubic. Calcite does this kind of orthorhombic thing where that's not 90 degrees and that's not 90 degrees. So it's a cool little mineral. Yeah, so that's crystals. Next up is covalent bonding. So I'm going to fix some stuff. And so covalent structures. Covalent structures, the thing to remember is that there's basically infinite different covalent structures because of the way that these things can attach to each other. It's not like ionic crystals where there's a specific ratio that minimizes the that neutralizes the charges. You can have, a bunch of different stuff. You can have H2O, which is water, and then you can have H2O2, which is hydrogen peroxide. You can have lots of different options. They form molecules. The molecules are self-contained, right? They're self-contained, but they are attracted to each other in various ways, which is what we're trying to talk about. This attraction normally comes from stuff like polarity, like this kind of thing, where the positives and negatives, think about it like a bunch of magnets. If you have a bunch of magnets, they'll all get attracted to each other. Then you can pull them apart and put them back together, but they're still individual magnets. That's what we see with water, and that's what we see with other molecules as well. Right? So here's some examples of different covalent structures, and these things can get really diverse. The word behind me there is just diverse. Really, really diverse. Like here's diamond over behind me there, and then this is caffeine over here. They all have a polarity. The polarity, almost all covalent structures have polarity, unless it's the same two atoms. So like we saw earlier, hydrogen and hydrogen together is just a lump. Hydrogen and chlorine, though, you have an uneven lump. And whichever side has more electronegativity will be more negative for obvious reasons, because the electrons are going to get pulled more that way. We have this concept of a dipole moment. Dipole means two poles. Think about it again, just like magnets. There's a north and a south pole, but here there's a positive pole and a negative pole. These are not full positives and negatives. They're partially positive and negative. That's what the little delta in front of it is. Delta comes from the same as like in math, delta y and delta x, except this is a lowercase delta instead of an uppercase delta. So it means it's a little bit positive or a little bit negative. And that tells us how these things are going to arrange themselves, because we can end up with a polar molecule or a nonpolar molecule. I'm going to go back over to mol view and give you an example of this using the same kind of demo I did with the sodiums and the chlorines, but with water molecules instead. So I've loaded up a bunch of waters. I've made a bunch of waters in all kinds of random orientations. We'll go to the 3D, and Mulvey is going to put them all together like this. Here's a bunch of waters right there. There they all are, kind of hanging out. And we're going to do the same thing. We're going to hit energy minimization and see what happens. Calculation in progress. They're starting to wiggle. I might have put too many waters on here. I might have maybe put too many waters on here. I think I might have made this a little too much. Let me go back to the 2D. We'll delete some of our waters. Let's take out like a solid half of them. Maybe make the computer a little bit, maybe make it a bit easier on the computer. Okay, back to 3D. Okay, so now we just have like 10 waters, and we'll go energy minimization. Let's see what happens. You can see some of them rotating. I'm not sure this is going to work properly. This doesn't seem to work really well. I'm going to play around with it, and I'll pause, and then I'll come back when I get a good result. So with 6, I got a pretty decent arrangement. You can see the water there, that the negatives on the oxygen are kind of coordinating to the positives on the hydrogen. That's after I clicked energy minimization a bunch of times. So that's what we see with molecular structures, is they get attracted to each other based on their dipole moments. There's a lot more about this in grade 12 chemistry, so it's a good kind of primer for what we're going to see there. We have this concept of a net dipole moment, which I'm going to go over to the camera for. When you have a net dipole moment, let's take water for example. Water has this bent structure. It's bent because of these lone pairs up here that push down on the bonds. We end up with our bond dipoles, right? Bond dipoles are going to go towards the oxygen. The oxygen has an electronegativity of about 3.5, and the hydrogen has an electronegativity of about 2.2. So we've got this strong bond dipole up towards the oxygen, right? Which means that our net dipole is going to look like that. There's our net dipole. Compare that to something like carbon dioxide, where the carbon is a 2.5 and the oxygen is a 3.5. But the dipoles are in opposite directions. So it's almost like, two teams of tug of war with the same pull both ways. So there's no net dipole. This is a big part of the reason why carbon dioxide is a gas at room temperature, whereas water is a liquid. Carbon dioxide is much bigger as a molecule, much heavier, but it's a gas at room temperature because there's none of this kind of dipole interaction that brings them together like magnets do. Right? It's very easy to pull them apart, to pull carbon dioxide away from other carbon dioxide versus pulling water away from other water, because water has these poles that are attracted to each other, whereas carbon dioxide does not. Now note, that's only for two water molecules that are next to each other, and they're going to arrange themselves kind of like this, right? Net dipole, they're going to get attracted kind of like that. That's what you're pulling apart when you're boiling water and stuff like that. It's a common misconception people have, that when you boil water, I guess somehow they think that it's the bond itself that breaks, but no, it's the two waters are just pulled apart from each other, and it's still H2O, it's just gas form H2O. Or if you freeze it, it's now just solid form H2O. So that's what we're talking about here, and that's the net dipole moment. Next up, we're talking about melting points and intermolecular forces. So I'm going to pause. This is a trend that we observe in melting points. This is going to be something called intermolecular forces, and please, please, please note that intermolecular means between separate molecules, between two molecules. Like intermarker forces would be these two markers, and the force between the two markers. Not within the marker, right? Not one marker, two different ones, and whether they're attracted or repelled from each other. Same thing with intermolecular forces. Just like I'm talking about, just like I was talking about over here, where there's intermolecular forces between the two hydrogen molecules, right? Intermolecular, between two of them. Very commonly in grade 11, I'll have students tell me that something within the molecule is what's giving it a high boiling point or a high melting point, and that's just not true. When we boil or melt something, we're not changing its molecular formula. It's a physical change, not a chemical one. But there's these general trends in melting points that we've observed. Ionic compounds tend to have very high melting points. So salt, for example, 801 degrees Celsius. Iron oxide, right? This is iron 3 oxide, but it's 1500 degrees, 1565 degrees Celsius. Molecular compounds tend to have relatively low melting points, but it depends on the size. Water melts at 0 degrees, sugar melts at 186 degrees. So kind of size also changes how it melts. And if it's non-polar, if it has these non-polar structures like nitrogen or iodine or carbon dioxide over here, this non-polar overall structure, it typically melts at a very low temperature, minus 195 for nitrogen. But if it's a big molecule like iodine's a big atom because it's way down the table, it melts at 114 degrees. So this is a non-polar molecule that actually melts at a much higher temperature than water. So this is all down to intermolecular forces. It's the attraction between molecules. So it's this green and gray stuff. Notice that it's between different molecules rather than within one molecule. Or it's these dotted lines here for the water. Ionic is the attraction between ions. It's a pure electrostatic attraction, just positives attracting negatives. Dipole is for molecular compounds, and it's the positive ends getting attracted to the negative ends. And if it's more polar, you get a higher dipole moment, you get more dipole force, you get a higher melting point. This is why ionic has such a high melting point, right? Salt or iron oxide, they melt at very, very high temperatures because the attraction is so great between the ions. To melt them, you have to rip the ions away from each other. You have to separate the ions from each other. Meanwhile, dipole, this is like a bunch of magnets. Right? So you're just taking the magnets apart. It's a little bit of a weaker force because for one, it's not a full positive or a full negative, and for two, they're a little bit further apart. They're not packed in as close. So that's the difference. That's why we see kind of a medium melting point when you've got a polar molecular compound. And the last piece is to explain why larger molecules tend to have bigger melting points. Bigger molecules have more attraction, like compare nitrogen to iodine, and you get this big difference in melting point, but there's no polarity, right? It's the same atoms, so they don't have a dipole. The answer to this is something called the London dispersion force, named after a guy named London, or the van der Waals force, named after some guy named van der Waal. It's a very weak interaction, and it explains how it can occur. To explain it, you have to remember that it's a cloud of electrons around this thing. And every so often, some of the electrons are going to be more on one side than the other. This is called an instantaneous dipole, right? It just by accident, some of the electrons are more on one side than the other. I like to talk about it in terms of my fish tank, right? I've got a fish tank back here. There's a couple of fish, right? Sometimes more of the fish are on one side of the fish tank than there are on the other side, just by random chance. And this creates a charge, right? This creates a dipole. Even though the bond itself is nonpolar, you get this dipole there. And what happens, because it's charged now, that dipole can influence other electron clouds, and it tends to make the electron clouds, the electrons will run away from a negative and run towards a positive, and when they do, that creates a negative and a positive inside this molecule, which is an induced dipole. And then that induces another dipole, that induces another dipole, another dipole, another dipole. So you get this very, very, very weak attraction between even nonpolar molecules because of this random nature of electrons. And it's very, very weak, but it's strong enough to create a difference. Once again, iodine, which is this huge, huge atom with a lot of electrons, when they're together, it's actually a solid at room temperature. Whereas nitrogen, which is much smaller, is a gas at room temperature. So size, bigger molecule and longer molecule tends to mean more attraction, tends to mean a higher melting point. But typically nonpolar molecules will have a lower melting point or a lower boiling point than polar molecules. Next up is solubility in water, which is, I believe, our last unit. Yes, it is. It's our last little piece of this lecture. So I'm going to pause and fix this stuff up. To talk about solubility, we're going to start with this quick video from the Canadian Museum of Nature. You'll be able to find it down in the description below, but it's going to explain how water dissolves salt. So we see this water molecule. We've seen a bunch of different water molecules. There's a salt crystal there. So you see the bonding, the intermolecular forces between the different water molecules back here, which is kind of cool. They're going to zoom in on the water molecule. There's a positive and a negative, positive side and a negative side. And here's the crystal, right? The positive and the negative. Remember that they're separate. They're just held together by electrostatic force. So what can happen here is the water can actually kind of sneak in and coordinate. The positive hydrogens will coordinate to the negative chlorine, and they can just pull it right out. For the positive sodium, the same thing happens, but now it's the negative oxygens that coordinate. And then the water surrounds the molecule, right? It surrounds the ion. And now they're stuck. They're kind of trapped inside that water. With lots of water molecules, they can come in and take away individual ions over and over and over and over and over again. And so this is how water can disassemble this salt crystal. Even though the forces are very strong, they're only strong because of the total of the forces together. rather than any individual force. So if you can pull them apart bit by bit, if you can divide and conquer, you can dissolve an ionic compound. So here's a picture of that, right? This is water dissolving, a positive and negative ionic compound. So water is quite good at doing this, especially if you've got common ions like sodium, potassium, chlorine, and fluorine. You get very soluble compounds with that. Also like nitrates and stuff. There's actually a whole unit in this course about solutions and solubility. It's unit 4. So if you wait until unit 4, we're going to talk a lot more about solubility. As we move towards the middle of the table, things tend to get a lot less soluble. So, if you got stuff like iron compounds or silver compounds, or especially gold compounds, they're typically not very soluble. So that's actually a good thing for us because they also tend to be kind of toxic when they're ions in water. But that's more of a unit 4 kind of thing. We'll talk about solubility in unit 2 and in unit 4. But you just have to understand that it surrounds. Water has to surround the molecule to dissolve it. Things get less soluble in the middle of the table. Molecular compounds usually not so soluble, with a lot of exceptions. That's not great. With a lot of exceptions. In particular, some of these exceptions are if you have compounds with a lot of OH groups or NH groups, because there's a lot of polarity there, the water can come in and surround the molecule. Remember, it has to surround the molecule to dissolve it. And small compounds, like ethyl alcohol, the alcohol that we drink, water has a very easy time surrounding it, especially because it has OH groups on it. I'm going to actually show you that in MolView. So I've made a bunch of alcohols here. The OH defines the alcohol group. If I hit this button, you'll see all the hydrogens around too. We'll go to 3D. Here they all are. You see they just get longer and longer and longer. For some reason, I put the methanol, in the middle, but that's fine. I'm going to hit that opaque thing, and it'll give me the kind of charge distribution on these, right? Remember that water has this positive negative thing going on, and it likes to surround molecules. So it tends to be attracted to positive charges and positive sides and negative sides on molecules. So you can kind of see from this that the small alcohol is going to be a better target for water, because there's areas where the water can coordinate to positive and negative and surround it, because it has to be able to surround it to dissolve it. The longer alcohol, right, this is ethanol, the one that people drink, is also pretty good on that front, right? There's a good amount of places for water to kind of get attracted to. But when you get out to the longer ones, there's this kind of area on the backside that's kind of in lumpy potato mode, and water's like, well, I don't know what to coordinate to there. So, once you get out past a certain number of alcohols, those alcohols become basically insoluble in water. But the small ones are more soluble. So, all that to say that molecular compounds are usually less soluble. Like those long alcohols aren't very soluble in water, but small ones and ones with a lot of OH groups are very soluble in water. And it shouldn't be that surprising because water itself is a molecular compound. So if something looks more like water, so more OH and small, it will tend to dissolve more in water. We call this solubility rule, like dissolves like. If it looks like water, it'll dissolve in water kind of thing. So that's how water dissolves things. And then the last piece is electrolytes. You guys might have heard of electrolytes. They're in sports drinks and stuff like that. What an electrolyte actually is just ions dissolved in water. The electro part comes from the fact that when ions are dissolved in water, they will conduct electricity in that water. Because if you put a negative on one side and a positive on the other side, which is what electricity is, right? It's electrons moving from negative to positive. The ions, the positive ions, the cations will get attracted to the negative side, and the anions, the negative ions, will get attracted to the positive side. And then the electricity will flow because energy can get transferred through the solution. So salty water will conduct electricity. But pure water actually won't. Here's water, and it's got a negative side and a positive side. When you put an electric current or try to put an electric current in water, the negative will kind of move towards the positive, and the positive side down here, the hydrogens, will try to move towards the negative, and it'll just arrange itself pointing towards one or the other. But because it's equal poles, because there's no actual charges here, it doesn't get pulled one way or the other. It just kind of sits there, and it all gets arranged in the right area. If you put enough electrical force, enough electricity into it, you'll actually rip the hydrogens away from the oxygens, and that's how they do electrolysis. That's how they make water. That's how they make oxygen on the space station. They'll actually take water and rip the oxygen away with negative on one side and a positive on the other. The oxygen will go towards the positive, and that's where they get their oxygen gas. But if you have a low level current, that's not going to happen. So pure water actually doesn't conduct electricity. But there's usually stuff dissolved in it that can conduct electricity. Right? So ions in the water are electrically conductive. And that's electrolytes. So when you put an ionic compound into water, it will conduct electricity. And the last piece here is polar covalent compounds. You know, they're covalent, but there's a positive and negative end. You end up with these kind of mixed properties. Like here's hydrogen iodide. Hydrogen iodide is this big old iodine and a little hydrogen, and the iodine is quite negative, and the hydrogen is quite positive. But it is a gas because the iodine is so huge that the polarity doesn't really affect this molecule too much. So melting point minus 51 degrees. It dissolves very easily in water because water actually provides enough force to pull apart the hydrogen from the iodine. And it turns into an ionic compound in water, which is kind of cool. It's molecular outside of water, but it's ionic inside the water. It's kind of a weird in-between. So there are compounds that kind of have mixed properties because of the influence of water. Yeah. And that's the entire lesson. So just to review what we did, we talked about electronegativity and polarity, and the fact that you can decide what kind of bond is going to be made by the differences in electronegativity. You know what, we'll actually go back to that. Here we go. The differences are, if there's more than 1.7, you get ions. If it's 0.4 to 1.7, you get this polar covalent, and less than 0.4, it's an even sharing, it's a non-polar bond. We talked about ionic lattices and why they make these structures and why these structures are so strong. We talked about why those structures are so brittle because of this stress fractures. Then we talked about covalent structures and how their properties are really dependent on this kind of dipole moment type stuff and size. Then we mentioned intermolecular forces. You have to know ionic, dipole, and dispersion forces and what creates them. We talked about solubility in water, how water actually dissolves things, and what it means to be soluble. And then briefly talked about electrolytes and how salty water will conduct electricity, but pure water won't. And then I just finished talking about the weird in-between polar covalent stuff, and how these aren't hard and fast rules, but they work pretty well for a lot of different compounds. So just like anything in chemistry, it was all created through experiment, and so the model is good, but there are always exceptions to it. All right, that's it. Thanks for watching, and I'll see you guys in class.